In the last two lectures, we have discussed reflexive spaces. By a reflexive space, we mean a nonlinear space for which natural embedding is odd 2. Today, I will continue the topic. Today, I am going to prove a very important theorem related to reflexive spaces. That theorem states that let X and Y be isometrically isomorphic nonlinear spaces over the field K, where field K is nothing but the field of real numbers or the field of complex numbers. If Y is reflexive, then X is also reflexive. Let us prove this theorem. Since it is given that X and Y are isometrically isomorphic, so let T is a mapping from X to Y, and this mapping is an isometric isomorphism. That means T is bijective, T is linear, and T is an isometry. That means T preserves norms. Next, we show that X star and Y star are also isometrically isomorphic. So let T naught from X star to Y star be a mapping defined by T naught F of Y is equal to F of T inverse Y for every Y in Y and F in X star. Let me make it more clear. Since T naught is a mapping from X star to Y star, so for any F belongs to X star, T naught F must be a mapping from Y to K. That means for any Y in space Y, T naught F must map Y to some element of K. And here we note that since T is bijective, so T inverse exists, and T inverse is a mapping from Y to X. So T inverse Y is a unique element of X, and since F is a mapping from X to K, so F of T inverse Y is a unique element of K. So here T naught F maps every element of Y to F of T inverse Y. And here we also note that since F belongs to X star, this is a bounded linear functional, and since T is an isometric isomorphism, so we know that it is a homeomorphism, so T inverse is continuous, and that means T inverse is a bounded function. And we know that composition of any two bounded function is also a bounded function, and so F composition T inverse is a bounded linear functional. Why? Because here T inverse is a mapping from Y to X, and F is a mapping from um, X to K. So F composition T inverse is a mapping from Y to K, and so F composition T inverse is a bounded linear functional on Y. And so we have defined T naught as T naught image of F is equal to F of T inverse, which is a bounded linear functional on Y. So this mapping is well defined. Next, as we want to show that this is an isometric isomorphism, so first we show that T naught is linear. So for F G in X star, alpha beta in K, T naught image of alpha F plus beta G of Y is equal to, by this definition, alpha F plus beta G of T inverse Y. And this is equal to alpha F T inverse Y plus beta G of T inverse Y. And that can be written as alpha of f of t inverse y plus beta times g of t inverse y. And by definition of t naught, f of t inverse y is nothing but t naught f of y. So we have alpha times t naught f of y plus beta times t naught g of y. And this is equal to alpha t naught f plus beta t naught g of y for every y in y. And so we have shown that T naught is linear. Now we show that T naught is 1, 1. For f and g in x star, let T naught f is equal to T naught g. And since T naught f and T naught g are mappings from y to k, so they must map every element of y to the same element. And so we can say that T naught f of y is equal to T naught g of y for every y in y. And so by definition of T naught, we have f of T inverse of y is equal to g of T inverse of y for every y in y. As T is 1, 1 and on to, T inverse y is a unique element of x for each y in y. So we can replace T inverse y by x, and so we can say that f of x is equal to g of x for every x in x. And this implies that f is equal to g, and so T naught is 1, 1. Next, we show that T naught is an isometry. For f in x star, we know that norm of f is supremum of mod of f of x, where x belongs to x and norm of x is equal to 1. As we know that every element in x can be uniquely written as T inverse y for some unique element y in y. So we can write it as supremum of mod of f of T inverse y, where y belongs to y, and norm of T inverse y is equal to 1. That means we have replaced x by T inverse y. And since T is an isometry, so T inverse is also an isometry, we have proved earlier. And so norm of T inverse y can be replaced by norm of y. And so we have supremum of mod of f of T inverse y, where y belongs to y and norm of y is equal to 1. And by definition of T naught, we can write it as supremum of mod of T naught f of y, y belongs to y, norm of y is equal to 1. But then this will be equal to norm of T naught f. And so we have shown that for any f in x star, norm of T naught f is equal to norm of f. That means T naught is an isometry. Now we show that T naught is onto also. So let H belongs to Y star. Then there exists F is equal to HT in X star. Here we note that YHT is in X star because T is a mapping from X to Y and H is a mapping from Y to K. So HT is a mapping from X to K. So this mapping is from x to k, and we also note that this is a bounded linear functional because t is linear, h is linear, and their composition is also linear. T is a homeomorphism, being an isometric isomorphism, so T is a homeomorphism. So T is bounded, H is bounded, and so their composition is bounded. So HT is a bounded linear functional, and so on X, and so HT belongs to X star. So there exists F is equal to HT in X star such that for each Y in Y, T naught f of y is equal to f of T inverse of y by definition of T naught. And if we replace f by ht, then we get ht of t inverse y, and this is same as h of t inverse y. And since t inverse is the identity mapping, and so we have h of y, and this holds for any y in y. So we can say that for h in y star there exists an element ht that is equal to f, such that t naught image of f is equal to h. So t naught is onto. Thus we have shown that t naught is an isometric isomorphism. Now we want to show that x double star is isometrically isomorphic to y double star. So we define a mapping T1 from x double star to y double star such that for phi in x double star, for g in y star, T1 phi of g is equal to phi of T naught inverse of g. Let me make it more clear. For phi in x double star, T1 phi must be an element of y double star. That is, T1 phi is a mapping from y star to k. So T1 phi of g must be a unique element of k. And here we note that since T naught is an isometric isomorphism, so T inverse exists. T inverse is a mapping from y star to x star. So for g in y star, T naught inverse of g is a unique element of x star. And since phi is the mapping from x star to k, so phi image of T naught inverse of g is a unique element of k, and so phi 1 T1 phi is a mapping from y star to k. And here we can check this T1 phi is also a bounded linear functional, because here we have shown that T1 phi is equal to phi T naught inverse, and since T naught is linear, so T naught inverse is also linear. Phi is linear, and so their composition is also a linear mapping. And since T naught is bounded, because we know that T naught is a homeomorphism, being an isometric isomorphism, so it is continuous, and so this is bounded, and T inverse is T naught inverse is also bounded, and phi is bounded, and so their composition is a bounded linear functional. So this mapping is well defined, and this mapping is similar to the mapping T naught. So like T naught, it can be easily shown that T1 is an isometric isomorphism. Now we want to show that X is reflexive, means we want to show that natural embedding from X to X double star is onto. Let pi X is a mapping from X to X double star, and pi Y is a mapping from Y to Y double star, and these mappings are natural embeddings. Here we have replaced pi by pi X and pi Y because we have two natural embeddings. As Y is reflexive, so we know that pi Y is onto. And as we want to show that pi X is onto, so we take an element phi naught in X double star, and we want to show that there exists some element in X such that image of that element under pi X is phi naught. So we claim that there exists X naught that is equal to T inverse of pi Y inverse of T1 phi naught in Y, such that pi X of X naught is equal to phi naught. So we have to show that image of X naught under pi X is phi naught. And here we can check this element x naught is an element of x. Why? Because t1 phi naught, because phi naught is an element of x double star, and T1 is a mapping from x double star to y double star. So T1 phi naught is an element of y double star, and pi y is pi y inverse is a mapping from y double star to y. So pi y inverse of T1 phi naught is a unique element of y. And since T is a mapping from x to y, so T inverse is a mapping from y to x, and so T inverse of pi y inverse of T1 phi naught must be an element of x. So this x naught is an element of x, but we want to show that image of x naught under pi x is phi naught. We know that for each f in x star, pi x of x naught of f, that is equal to phi x naught, because we know that pi x of x naught is phi x naught by definition of natural embedding of f. Pi x naught of f is equal to f of x naught. We know this definition of phi x naught, so we have f x naught, and this is equal to f of, and here we write x naught is equal to T inverse pi y inverse T1 phi naught, and this is equal to T naught f by definition of T naught mapping. F T inverse of something is equal to T naught f of pi inverse pi y inverse of T1 phi. Here we are using definition of T naught f. As pi y from y to y double star is 1 1 and on to, so for T1 phi naught in y double star, there exists a unique element y in y such that pi y of y is equal to T1 phi naught, because this pi y mapping is 1 1 on to, and we know that T1 phi naught is an element of y double star, and so this and since mapping is onto, so there exists a unique element y in y such that image of y under pi y is equal to T1 phi naught, and this implies that y is equal to pi y inverse of T1 phi naught. Here we note that since pi y is 1 1 on 2, so pi y inverse always exists, and so here we can write y is equal to pi y inverse of T1 phi naught. We know that for any f belongs to x star, T naught f belongs to y star. Why? Because T naught is a mapping from x star to y star, so T naught image of f belongs to y star. And we also know that pi y of y is equal to phi y. And since pi y of y and phi y are elements of y double star, so these are mappings from y star to k. And since these two mappings are equal, so they map every element of y star to the same element. And so pi y of T naught f is equal to phi y of T naught f, because T naught f is an element of y star, and this is equal to, by definition of phi y, this is equal to T naught f of y, and since y is equal to pi y inverse of T1 phi naught, so we can replace y and we will have pi y of pi y inverse of T1 phi naught of T naught f is equal to T naught f of pi y inverse T1 phi naught. And since pi y inverse is an identity mapping, and so we have T1 phi naught of T naught f is equal to T naught f of pi y inverse of T1 phi naught, and we mark it as 2 using 2 in 1 here. For ready reference I have given 1 which is pi x of x naught of f is equal to T naught f of pi y inverse of T1 phi naught, and so we get pi x of x naught of f is equal to, here we have T1 phi naught T naught f, and so if we use the definition of T naught T1 mapping, then we have phi naught T naught inverse of T naught f, and since T naught inverse T naught is identity mapping, so we have phi naught of f for any f belongs to x star, and so we can say that pi x of x naught is equal to phi naught. We have shown that for phi naught in x double star, there exists x naught in x such that pi x of x naught is equal to phi naught. So pi x is onto, hence x is reflexive. Thank you.